Hello everyone. Today we are going to study about digital image processing's another subchapter, and in that we are going to study about the spatial filters for sharpening operators, convolution and correlation. We are also going to study about the objectives of integration, differentiation, application of sharpening, and also we are going to see the first order and second order derivative operators and their responses, Laplacian operators and Unsharp Masking. So coming to the process, at first you know that spatial filter we have been studying for so long. So far we have seen the introduction about the spatial filtering. So you know what is spatial filtering is? Spatial filtering basically means the space, or it basically corresponds that how we are operating something on pixel level. That is your spatial filtering. So you know that so far we have already studied smoothing, and right now we are going to see about sharpening. Okay, in the forthcoming chapters we'll be seeing about the next part, and that is your feature extraction, edges, lines and corners. So spatial filtering is basically operates on directly on pixels, as I told you now. A small matrix, kernel or mask slides over the complete image. So output pixel is computed using neighboring pixel values. So in that, neighboring pixel values will be involved. So sharpening filters are designed to enhance edges and fine structures. So basically, to understand that, we should understand what is kernel and mask first. So kernel and mask are actually the same thing, just the names are different. So that kernel and mask is nothing but, you can see that, for example, in this complete image, if we have to operate something on a small level, on a smaller part, what we'll do? We'll select that area. So, okay, and in that the operation will happen. So that particular area, and whatever operation you are doing in that, that will be replicated over the complete image, and that will be your and that area which is selected initially where the changes will happen, that will be your kernel and masks. So you can see that complete processing will happen to the overall image as it is happening in the GIF. Then whatever is operated there, that same thing will be operated for the same way it will be operated for the complete number of pixels in the image, and the output will be the clearer image, you can say, by using spatial filtering. And now we are using for sharpening. So in that, the process is convolution and correlation. So convolution and correlations are actually very important topics in digital image processing. You will understand with so many examples today. So convolution and correlation is nothing but, in that there is a difference of kernels. So like when you are applying the kernel, what you basically do, you rotate it 180 degree. In the case of, you can see, in the case of convolution, kernel is flipped. In the case of correlation, kernel is not flipped. For example, if you have 3 2 1 kernel, it will become 1 2 3 in the case of 180 degree flipping, and in the case of convolution. So let's see correlation first. So in correlation, kernel is applied directly without any flipping, and it used manually in the template matching and feature detections, and output depends on kernel orientation. And in the case of convolution, kernel is flipped horizontally and vertically before applying. It's used in most image filtering operations, and it ensures consistent mathematical behavior. So this was theory. It will get much clearer when we are seeing the practical things. So you can see, for example, this image, the convolution and correlation, you can see that they are opposite to each other. Whatever identification you got here in the case of kernel, in the case of correlation, that opposite of that, you can see that that is flipped, no, 180 degrees. So behind that structure also you can see in that case. So let's see here. So you can see that in the case of correlation, you don't have to do flipping, and in the case of convolution, you have to do flipping. Then side kernel, as it is, it will be applied in the case of correlation, but in the case of convolution, it will be flipped. So in computation, you can see that it multiplies and sums. In the case of convolution also, it basically multiplies and sums. It means to say that with the kernel, we multiply and add the computation process. You will be seeing that in the next thing. So output difference will be, it's a correlation is directional, it's a sensitive, and convolution is directional aware. Correct orientation is actually obtained here. So let's see the numerical, then it will be much clearer to you. So for example, we have the question in that, don't consider the question as very tough, because you can see that I is the image and K is the kernel. Just understand two things we have. One is your image, and image is one dimensional. You know that one dimensional images will be like in a single line, two dimensional image will be like your picture, and three dimensional you already know. So since we have only rows here, so that is one dimensional image you can see. So 10201 and the kernel is 213. So what we have to do initially, first we have to perform the correlation, okay, then we have to do the convolution, and then we have to compare the outputs. So what difference you basically got, okay. So this is the only question. So at first we need to find the zero padding. So what is zero padding? Zero padding is nothing but from the pixel, the outer layer is zeros. Okay, we consider it as a no value. So that zero values we have to find. So you can see that our question is written as first, that here this is our image and this is your kernel, and what we have to do, we have to apply since the kernel size is 3, because you have 3 elements, 2, 1 and 3. So kernel size is 3, so zero padding will be 1. How? So for that we have a formula. The formula is padding equal to k minus 1 by 2. So you can see that if kernel is 2, 1, 3, so 3 values are there. So 3 minus 1 by 2 is equal to 1. So 0 padding will be 1. So because of that, 1 0 will be applied behind and 1 0 will be applied after from the actual image. Okay. For example, if the kernel size is 5, for example here 2, 1, 3, 2, 5, that is the kernel size, then in that case what will happen? 5 minus 1 by 2, it means 2 value will come. So here 2 zeros will be applied. Here also 2 zeros will be applied. Since this is one dimensional image, we can say that kernel mask is 3, so we will be applying only 1 0 on the top and 1 0 in the end. Okay, so that is the thing. So in this image actually we are applying that. Okay, you can see this is your input image and this is your padded image. Okay, coming to the conclusion, calculation, the calculation is very easy. So what you can see, that this is your I padded value and this is your kernel mask. Just the multiplication will happen. This 0 will be multiplied with 2, this 1 will be multiplied with 1, and this 0 will be multiplied with 3. So let's see. So for the first shift, what we have to do? We have to calculate this 0, 1 and 2. We have I padded value, and then we have kernel mask. So 0 will be multiplied with 2, and 1 will be multiplied with 1, and 0 will be multiplied with 3, and that all the calculations you can see here. Okay, so this is your first shift, this is your window. So window is 0, 1, 0 that we have written here, and this is your calculation. So 0 is multiplied with 2, 1 with 1, 0 with 3, and you are getting all the additions. Answer is 1. Okay, then we'll go to second shift. So in the second shift, what will happen, that your this calculation will shift towards right. Okay, so one, it was first, then it is second now. So in that case, what will happen? 1 will be multiplied with 2, and 0 will be multiplied with 1, and 2 will be multiplied with 3, and this answer will be coming. Okay, so ultimately you will be getting this value 8. Then for the third shift, what will happen? Again it will be shifted towards the right. Okay, and that 0 will be multiplied with 2, 2 will be multiplied with 1, and 0 will be multiplied with 3. So answer will be 2. So that only we are getting here. Okay, likewise you have to keep it shifting and you will be getting the values. Okay, so this was for correlation. In correlation there is no shift of, you can see that there is no 180-degree rotation of kernels. So whatever was written in the question, that only we are straight away using. Okay, in the case of convolution, okay, before going for convolution, you see that the y correlation value is 18271. This is important, you should write like this. Okay, moving to the convolution. Okay, now we have kf, so kernel flipped. This red color f represents flipped. Okay, so now instead of 213, now this is 312. Other everything is same. Okay, so what we have to do, we have to select for the first shift, we'll be selecting this 010, and instead of 213, now we have 312. So 0 will be multiplied with 3, 1 will be multiplied with 1, and 0 will be multiplied with 2, and all will be added, and you will be getting this value. Then again for the second shift, the same process. What will happen here? It will be moved toward the right side. Again 1 will be multiplied with 3, and 0 will be multiplied with 1, and 2 will be multiplied with 2, and you will be getting this value. Okay, for the next shift, again the same process happened. You are getting 2. For the next shift, again the same process happens. You get 8, and for the next shift you are getting 1. So y convolution value is 17281. So we have convolution value and correlation value also. So these are the movements. You can see how it happens when the convolution versus a correlation happens in the real time. Okay, so this was convolution and correlation. Objective of spatial filtering. So what is the objective actually? Objective is like applying integration, differentiation. So all these things we are applying, and then we are seeing that how the values are coming. So in the case of integration, what we see, integration actually affects the output in the form of smoothing and averaging. So the main concept is it integrates neighborhood values and it reduces noise and small intensity variation and acts as a low pass filter, surpasses the high frequencies. Means you can see that result will be coming now. For example, we have our kernel mean filter. Let's apply some filter to that one. So we are applying a mean filter, and in that case, what happens? This is the input image. So these first one is your kernel, and second is your input image. When we apply these two, what happens? So you see, you can see that 1 multiplied with 120, 1 multiplied with 122, 1 multiplied with 121, 1 multiplied with 119, 1 multiplied with 125, and since 1 by 9 is there, so that also will be available here. So that will be average of all these values, and you are getting the output as 123. So what happens here? 125 is reduced to, you remember one thing, that always these type of values are applied in the center pixel. Okay, so now this 125 will be replaced by 123. So what happens? It actually reduced the value. Okay, so because of this, what happens, that image becomes much smoother, and because of averaging. Okay, so whatever image it was looking very high intensity to you, that becomes smoother now. Okay, the visibility actually gets adjusted as per our eyes. So what is the effect? Noise reduction. It smoothens the region, but actually there is a drawback, that it slightly blurs the edges. For example, whatever values are there, it's like for example, it is 255, totally dark white, right? That will become 220. Okay, so that value of the brightness will reduce in the corners, so that will look like little blurred image, but ultimately it smoothens the complete image. Okay, you can see here the effect. Okay, you can see the corners. In the corners were very dominant before, but now they are not dominant. So that is the effect of integration, you can say. Okay, now we'll go for differentiation and edge detection. And what is the concept behind this? It computes rate of change of intensity that I was talking initially, and it highlights the edge and boundaries, and it acts as a high pass filter. So whatever was happening before in the case of integration, what was happening? Edges and boundaries were becoming smoother, but here edges and boundaries are becoming dominant. Okay, so you know that the opposite of integration is differentiation, not totally but roughly. Okay, so you can say that whatever is not happening there, that is happening here. So based on our input, we can apply differentiation or integration in the image processing. So let's see, we'll take the example of Sobel operator. Sobel, you know that Canny, Sobel and Privet are the different edge detection techniques. So one of them is actually Sobel. So for this, the values are -1, 2 and 1, 0, 0, 0, 1, 2, 1, and you know that the input image is here. So how we apply this one? So the process is very simple. Whatever matrices we are getting, we'll be multiplying the elements with that one. We'll be doing the addition, and whatever the central pixel value is there, that will be changed from the older value to new value. So 121 will become newer value. So let's apply this. -1 will be multiplied with 120, this 0 with 122, 1 with 125, -2 with 118, and 0 with 120. So corresponding values will be multiplied and added. So ultimately, if you do like this, you'll be getting the value as 40. Okay, so now you see 121 became 40, right? So now what will happen? The value of intensity reduced, it dropped. Okay, so edges becomes prominent and structural details becomes highlighted and noise is amplified. Okay, that is a drawback actually here. So you can see that edges become dominant. You can see the edges very nicely. Okay, structural details will become highlight. It means that whatever that edges are there, the corners are there, that will become highlighted. But the main problem is noise also gets amplified in this case. You can see in this case, wherever the edges were there, they are highlighted now. Okay, compared to the case of integration. Okay, moving forward, we have application of sharpening. So the third is your sharpening. So it enhances the edges and fine details and adds high frequency components back to original image, and it improves the visual clarity. That actually happens here. So for that, we'll take the example of Laplacian, your Laplacian based your sharpening. We'll be taking example. So the question is, you should remember this formula for this one. This is a Laplacian formula: f of x comma y minus delta of square f of x minus y. So what is this? Don't get confused that this is square or something. So this f of xy represents, you can see here, this is our input image and this is our Laplacian kernel. So what we are doing here, basically, whatever the central values are there, okay, this is central value, that should be multiplied with 4. Okay, so that we are making it 4 because that gets multiplied directly with this one. Okay, so we have 4 into 125 minus as per the formula, this minus is coming, right? So minus, and we'll be multiplying with your all the values. Either you can multiply with minus 119, minus 1 multiplied by 122, minus 1 multiplied by 119, minus 1 multiplied by 120, minus 1 multiplied by 123. Or you can commonly multiply, that also is possible. So that only they have done here, and answer is your 16. Okay, so the final answer is 16. So now what is happening? So this 125 we have to add with 16 here. That is the difference in Laplacian kernel. So whatever value is coming, that will be increased by 100 and it will be increased by 16. So it becomes 141. Okay, so that is the process of applying. So what effect it will give? Now edges and details both are enhanced here. So that is actually, you can see that is a trade-off. Okay, it images looks crispier, and over sharpening may cause halos. You know that the wrinkle effects will come, like it will that will not it will just reduce the clarity of some parts. So that is the drawback basically. So input image, you can see that input image and sharpened details. Okay, so sharpened details are much clearer compared to the input image. Okay, so these will be the output effect of application of sharpening. So in summary, you can see that in the case of integration, in the case of differentiation, and in the case of sharpening, so we have applied in the case of integration, we have done the smoothing, then edge detection using your pivot, with using Sobel, and in sharpening we have applied the Laplacian. So mean value is 123, gradient response is 40, and Laplacian response is 16. Those are the results we got. Okay, so central pixel becomes 123. Okay, and instead of 125 it became 123, and central pixel became 40. So edges became stronger, and central pixel became 125 plus 16, 141. So instead of 125, now it is 141. So we applied on the same image all the three values and see that whatever the result it gave. Okay, so for effect on image, you can see that noise reduction happened here in the case of integration. Smoothing regions also increased, and but the problem is slight edges got blurring. Okay, opposite of that, edges are boundaries are highlighted and fine details extracted and noise amplified. Actually that happened in the case of differentiation, and sharpening, edges and fine details are both are enhanced, and it improved the visual clarity. And over sharpening may cause halos and noise, but if you compare all of them, the last one is actually giving you the better result. Derivatives in digital image processing. So the derivatives in digital image processing basically have the first order and its second order, and it's a Laplacian operation and Unsharp masking. So basically how we apply these things in real time, that we are going to see. So in digital images, pixel intensities are discrete. So derivatives are approximated using finite differences. Derivatives measure rate of change of intensity. As we know, we have been studying from a very long time that derivatives basically means the rate of change of intensity or rate of change of any value. So in the case of image processing, that is your rate of change of intensity. So higher value of derivative will give you that abrupt changes, lower value of derivatives will give you lower changes. So areas of rapid change corresponds to edges, lines, and fine details. It means they want to say basically that if in an image, if sudden variation is coming to the particular point in the image, it means that that particular point is either edge or a line or fine details. So that details need to be highlighted to see as per your requirement. So derivative operations are actually fundamental for basically where we apply these derivatives: for edge detection, for feature extraction, and image sharpening. Wherever the image quality or image content or our region of interest needs to be highlighted, in that case we go for derivatives. So the main important concept is, if image intensity changes slowly, derivative is small. If image intensity changes abruptly, derivative is large. That's what I told you before, that if any particular change is very high in the value of derivative, it means that there is a huge variation in the image. Okay, so you can see here. So these outputs we'll be seeing now. Okay. So first order derivatives, that is to identify, actually that is basically operates on gradient. Okay. So what is the concept? So first order derivative detects how fast brightness changes. So basically first order derivative, if you apply, you can identify that how much is the change in the brightness value. It is used mainly for edge detection, and you can see that gradient value of this delta of f is actually nothing but a gradient of your pixels. Okay. So g of x plus g of y written like this also represents root under g of x square plus g of y square. So basically output is actually, it is strong responses at edges. You will be getting the better edges. Direction of edges also you'll be able to identify, but this is also sensitive to noise. If you only can imagine that if any image is not very clear, if any some mistakes are there, some dots are there, or some corruptions are there, in that case what will happen? Edges will not be able to identify, right? You'll not be able to identify the edges. So where it is implemented in real time are lane detection in self-driving cars. Like when you're driving the self-driving car, and automatically it has to identify the lane. So what it basically does, it follows the lines. That white color line is there, no? That also it reads. So where the black becomes white, that edge should be identified by the system. So this is used there. Text edge detection in document scanning. If you scan the document, so this circle is actually O. How it will identify? By the edge. Face feature extraction in cameras. Yeah. So if you have a facial expression, that also it will be identified. So first order edges will give you the result something like this. From eyes you won't be able to see clearly, but you see that in the complete structure, it's giving you the highlighted circle. Yeah. Okay. So the practical first order operators are Sobel and Privet edge detection techniques. They use this one. Okay, so Sobel operator combines differentiation and smoothing, and based on that it identifies the edges. Why Sobel is popular compared to Privet and Sobel? Sobel is popular because it's more robust to noise compared to Privet, and it produces continuous edges. Means it will, for example, if any edge is identified, the complete structure will be completed. Like for example, if a circle is drawn, the circle will be completed. It won't be broken. Okay, so those things it will do. So examples are industrial defect detection, MRI boundary detection, and smartphone edge detection enhancement before display. Yeah. So you can see like this, it will give you, Sobel will give you the edge output. Second order derivative are nothing but the change of a gradient, but it highlights fine details. Okay. Before we were only, if you go for first derivative, it will give you the edge clarity. But if you go for second order derivative, it will give you fine details also in the thin edges. Okay, those thin edges, those were not highlighted in first order derivative, those also will be highlighted here. So what all the responses? You can see that response strongly to fine structure, that very fine lines, those you are not able to identify, those you will be able to identify here. Zero crossing indicates edge locations. It means that the corners, and very sensitive to noise, and no edge directional information. So basically what happens, these are very sensitive to noise. Why we say that? Because this will be amplified. Whatever noise will be there, that also will be amplified, and that will corrupt the values. So that is good if we are having an image that is very clear to you. So real-time examples are microscopy, detecting fine stretches or materials, and highlight fine texture in satellite images. So satellite images, if you are taking, in that you need to do multiple your amplification, multiple resolution enhancement. In that case, these are actually useful. So you can see here, output will be very clear. Okay. Then we have Laplacian operators, core of sharpening. So main core of sharpening is actually Laplacian operator. Laplacian operator is a second order derivative that responds equally in all directions. Okay, it highlights a region of rapid intensity changes. So wherever it's finding that its intensity is changed, that place it will particularly highlight. Okay, so the formula is delta square of f equal to dou square f by dou x square plus dou square f by dou y square. So change in the value, in terms of x and y. For example, if you complete pixel value is there, the function is made up of pixels. So what changes are happening in x and what changes are happening in y, in terms of x and y, that will be identified and added. So you can see the response. It highlights the fine details. It's used for sharpening, and it amplifies the noise also. That is the problem. So real world examples are medical imaging, document enhancement, and satellite image sharpening. This is used there as well. So now you can see the difference. So the main difference is in the corners it's actually highlighting too much. So where the intensity changes, so that area will be highlighted to the rapid changes area will be mainly identified. Okay, so this you can identify a lot of things with this one. Okay, so how we do this one? So Laplacian is a second derivative that responds equally in all directions, that you already saw. So you can see that one more example. You can see the sharpened settings, highlighting features, and enhancing roads in maps. That is also the practical example. You can see that. Yeah. So unsharp masking, we have another term, that is unsharp masking. Unlike the name, actually unsharp masking actually increases the sharpening. Name is unsharp, but it increases the sharpening effect in the complete image. So how real software sharpens the image? That is basically based on unsharp masking. So the main concept is unsharp masking is a spatial image enhancement technique used to sharpen an image. So you know that sharpening means. Sharpening means that if any image is there, in that image should look crisp. It should not be like blur type. Okay, so that crispiness comes in the image using unsharp masking. Despite its name, it increases sharpness by enhancing edges and fine details. It is originated in printing and published to improve perceived details. So whatever details we are seeing, that should be very clear to our eyes, and that crispiness will be coming from unsharp masking. So let's see how we do that one. So before that, we'll be having that why we use that in practice. It looks more natural in the image, and it preserves overall brightness, and it's used in Photoshop and mobile cameras. Okay, real world examples: photo editing applications, newspaper image enhancement, and medical image post processing. So let's have a look. Okay, so unsharp results will be giving you the better values. Okay, core idea we should understand. So it's first what we have to do. We have to take the input image. We should have the input image. Then we have to create a blurred version using a low pass filter. Generally we use a Gaussian. Then subtract the blurred image from the original to get the mask, and add this mask back to the original to produce a sharpened image. So basically what it does, takes the image and it identifies a blurred version of the image by applying mask and all, and then that it subtracts from the original image, and whatever value is coming, that it adds to the original image. So you can see that basically what happens. So at first we have the input image f of x, you can see that f of x of y minus f blurred. So the blurred version we are reducing from the original image, and what we do, whatever values we get, that we multiply with your k value, that is your the k value is actually high boost filtering coefficient. So that value we are, or you can say that scaling constant. So that we are multiplying and we are getting the result. So you should understand these two first. So mask equal to f of x of y minus f blurred of x of y. So first we need to find this f of blurred. Okay, so blurred image we are finding, then that we subtract from the original image, and that we multiply whatever mask value is coming, that we multiply with a constant 1 or 2 or whatever, and then that we add with the input image and we get the output image. So you remember this complete process that we are going to use. So here I have written g of xy is the output, f of xy is the input, and mask is the difference between original and blurred image, and k is the scaling constant. So when k is equal to 1, generally when the k is equal to 1, it gives you unsharp masking, and when k is greater than 1, then that is a new term that is called high boost filtering. We are applying high boost filtering in this one. Stronger sharpening will be the result of this one. Okay, so it depends on you what is the k value. Okay, so let's see the numerical. So this is our question. Okay, we have this input image. What do we have to do? We have to compute the blurred image. Okay, we have to compute the mask, and we have to compute the sharpened value. Okay, so our first question, after computing this one, the first question is to apply unsharp masking to the central pixel using 3x3 mean filter for blurred blurring and show all intermediate steps. Okay, these are the intermediate steps. So what you have to do, 125 will become something, so that you have to change here and you have to show the output, and apply high burst filtering with k equal to 2 and compute the new central pixel value. So when instead of that k value becomes 2, what result will come to this one? That also it wants to show. So let's see. So this is our question. Okay, in this question, this 125 is just a central pixel, and you know that if we apply the mask, this value changes. So that ultimately results into the some different image with better quality. Okay, so for that, this is your mask value. So your mask value is actually nothing but your mean filter we are applying here. So what we'll be doing will be, you know that the process 120, 122, 121, 119, 125, all will be multiplied with one each element. Okay, and will be divided by 9. So you can see that I have multiplied all of them, 120, 122, 121, and all will be added and divided by 9. Okay, that is the process to get the output, right? So answer is 123. So 125 became 123. So this is your nothing but f blurred value. Okay, note it down. Then mask details, you remember this formula. So what we are going to do, the value of original pixel was 125. Now what we got the blurred pixel value, and that is your 123. So the difference is 2, right? Now after this, what was the next formula? This was the next formula we were seeing. So f of xy plus k into mask x of y, so x and y. So in that case, we are getting the answer as f plus 1 into mask equal to, this is the formula. So 125 plus 2 will get. So you remember I told you that we'll be getting the input pixel. In that we'll subtract it from the blurred pixel, and whatever value is coming, that will add to the original pixel value. Okay, so that only is happening here. Okay, first what it identified the blurred value. So how to identify the blurred value? By using the mean filter. So with this it multiplied and they got the answer as 123, and then after that it subtracted from the original pixel and the value is 2, and that 2 it added to the original pixel. So you are getting 127. So 125 became 127, right? So because of that, what will happen? That your values, the visibility will increase. Okay, and the output will be much crispier and the clearer. So what is the interpretation? Central pixel increase from 125 to 127. So details enhanced. Okay, so you can see that if the value is more than 1, in that case what will happen? That will be called as high boost filtering. So we got the previous mask value as 2. Now what we'll do, instead of k equal to 1, when we apply 1, here we apply with 1, then the value becomes 127. Then this is the process of unsharp masking. But this 1 is 2, you can say when that is greater than 1, then that is called high boost filtering. Okay, and that will become 129. So you only imagine the details increased. Okay, so that will be the effect of your high boost filtering and your unsharp masking. Okay, so this is the things. Okay, so larger K is the stronger sharpening, and too large K is halos and noise amplification. So that is the thing. If the noise is there, that also will be amplified. So high boost keeps the original image strong and boost details more aggressively. So the main advantage is it enhances the edges and fine details, and it improves the perceived sharpness, and widely used in photography and medical imaging. The main limitation is actually it can amplify noises, and it over sharpening causes halos and dingings. Okay, so you can see this board. So value 1 and 2 you should notice. Okay, I hope you are able to see. The k equal to 2 actually increases the quality, but at the same time you can see that in the corners you can see that too much amount of brightness values are there, and that ring like structure is actually your halos. Okay, so you can see that this is the conclusion. So first order derivative, second order derivative, sharpening and unsharp masking. What are the theories are there? These are the theory values, and real world meaning is what? It first order derivative is to identify the edges like lane detection or text borders. Second order, same thing we can do, but it enhances the fine details. The same thing, but with much detailed output. Then sharpening, it makes image look clearer, but unsharp masking gives you practical visibility, like whatever enhancement is done in the image, but it's not done that much that it can disturb the image. So that will be achieved by using unsharp masking. Okay, so this was all about the complete class. Thank you very much.